Saxon's Trig, Lesson 17, Proofs of Pythagorean Theorem and Proofs of Similarity, beginning on page 127. So, all throughout your math career, you have been provided with a variety of rules, and you've basically been asked to accept them as truthful without proofs. In the Trig book, you get the proofs behind the rules, such as Pythagorean theorem, that you no longer want to really have because you have just accepted, yes, this rule works, mathematicians have used it, but in this book, they want you to have the reasons behind. So that's why we have a lesson that talks about going through proofs, and there are two proofs for Pythagorean theorem, and then more formal proofs for things with similarity. All right, so let's begin with our Pythagorean theorem here, and I went ahead and drew a diagram so that I could have stuff labeled. And I see that I've got a large right triangle here, a right triangle here, and a right triangle here. Now, we did before a chart that helped us kind of compare these similar triangles because they're all three right triangles. That's what I'm going to do here to make this proof work. So we've got our big triangle, we've got our right triangle, and we've got our left triangle. We have our hypotenuse, we have the little leg, and we have the big leg. So from the big triangle, its hypotenuse is C. For the big one, its little leg is A, and the big leg is B. For the triangle on the right, its hypotenuse is B. Its little leg is, oh, it's this one here, which I did not label as anything. I'm going to leave it blank. And then the big leg is the Y. On the one on the left, the hypotenuse is A. The little leg is the X. And the big leg is this one that's not named, so I'm going to leave it blank. So we know from before when we did these charts, we're looking for where I have overlapping letters. So I know I have that here with the A and here. So we can say C over A equals A over X. And if we cross multiply, that gives us A squared equals CX. Look for B's that are overlapping. That would be here and here. So we can have CB equals BY. And when we cross multiply now, we get B squared equals CY. And I have to stop and look at the original. This C and this Y here in the picture shows that if I add X plus Y, I get the length of C. So if I am adding these two statements together, I'm going to get A squared plus B squared equals CX plus CY. And if I pull the C out, that leaves me X plus Y. And what was X plus Y? A C. So if I substitute that in, that's C times C, which is C squared. A squared plus B squared equals C squared. Oh, there was my right triangle. Leg squared plus leg squared equals hypotenuse squared. There's the Pythagorean theorem. That is one way to prove it. Also, I can prove it by, and if you look on page 128, you get the diagram that I'm doing here. I have a large square, and I'm going to create another square, and I probably won't get this identical, but I'm trying to create another, yeah, it's not identical, another square inside. And so I need to label some parts here. This will be B, this will be A, this will be C. Because it's a square, this is also C, this is C, this is C. And these triangles are the same, so this one is labeled B, this one is A. I can finish labeling them. This one is B, this one is A, this one is A, this one is B. Okay, so once we're here, if I find the area of the large square, this side is B plus A. And that is multiplying with this side, which is also B plus A. And because I want to prove, oh, I guess I should label that 90 degrees and I should label that 90 degrees. They clarified, and it will be helpful to know that I am getting the Pythagorean theorem for the rule of a right triangle. I'm looking for the area of the triangle, which means I want to take out, for the area of the triangle, the area of the internal square. So I will minus, and how do I get its area? C times C, which makes it C squared. I'm going to go ahead and distribute here to create B times B is B squared. B times A is BA, or AB, plus A times B. I'm going to just write it the same direction, even though that's AB, plus A times A squared, minus the C squared, should be giving me the area for 4 triangles. And the area for those triangles are half base height. I feel like I'm not doing this fully the way they were. We should get the same idea anyway. Half base and height. Okay. So B squared plus, these are like terms, identical. So there are 2 BAs plus A squared minus C squared equals 4 times a half is 2AB. Now, since I know what Pythagorean theorem says, I know sort of where I'm headed. So I realize I need to put like terms together and put something on the other side of the equal sign, because if I move this 2AB over here, it's going to cancel off and leave me nothing on this side. So I know that I want to go ahead and move this C over here to fill in so that I get a statement B squared plus A squared equals C squared, the Pythagorean theorem that I was trying to do. And technically it's A squared plus B squared equals C squared, but we get the idea. So I can prove it based on that shape as well. Now they went through in the book the measure of certain angles, but then ultimately they got down to this algebra stuff. All right, part B, proofs of similarity. All right, we know that similar means same shape, but can be different sizes. So in a formal proof, I do not need to use the S, the side part, because the side being the same is what forces it to be congruent. So if I can prove 2 angles, I imply the third angle, and that is all I need to do similarity. So in example 1, it gives us a picture. ED, this one is marked as the same as this one, which is A. Center was C, and this one is B. I think I have everything marked. So it says prove that the 2 triangles on this side and this side are similar triangles. So we're going to need our statement and our reason. Obviously our first stuff is given. So what did they actually give me? The only thing marked in this picture is that angle A is congruent to angle E it was given. Can I find anything else that is the same in them? Well, no sides are matching up or aligning, but I do see I have intersecting lines, which means that this side here should match this side here, because they are vertical angles. So let's state that angle A CB is congruent to angle ECD because they are vertical. That's two parts. And because I don't need to prove a side, I only need to prove two angles, I have done what I needed to do to prove similarity. So triangle ABC is similar, no equal sign with that one, to triangle EDC. Why? Because of angle, angle, or you can say angle, angle, angle. Either way, you have it assumed. Now, they went through the extra step of saying that the third one has to be there, but you don't need to list all three because always that implied to gives you the three, and so I just take it as kind of redundant at that point. Example 2 on page 130 gives you a diagram, and it says this has an arrow, this has an arrow. That tells me they're parallel. B, C, D, E, oh, labeling's the same, and that's all it gives me. So it says prove that these two triangles are similar. We need our statement and our reason, obviously given. And the only thing they provided me was that A, B, I'll say segment. It could be line, either way. Segment AB is parallel to segment ED. That was given. All right, so what do I know based on the fact that I have parallel lines? Well, I see that this is a transversal this way, and this is a transversal this way. So if I'm using this one as my transversal, then this angle must match this angle, alternate interiors. Let's get those stated. So angle B is congruent to angle E. That's only one angle proven. I can do the same thing. Actually, I would just leave it in step 2 because the reason is the same. So that would give me angle A is congruent to angle D because they are alternate interiors. Now I've proven 2 angles implies the third. Oh, I could have said that this angle is congruent to this angle because they are vertical angles. I could have also done that, but the two triangles A, B, C is similar to triangle EDC. Why? Because I proved 2 of the angles, therefore implying the third. All right, their final example in this lesson gives 2 triangles, GHI with a 12, a 15, a 30 degrees, and then it does a smaller triangle. This one is labeled with the 30. This is J, K, and L, and 8 and 10. Prove that the 2 triangles are similar. All right, we need our statements and our reason. Obviously that line got in the way there. That's given. So what things did they provide for me listed here in the given? Okay, so they listed angle G is 30 and angle J is 30 degrees. That part's given. Also, they're jumping to a proportion. If the triangles are similar, their sides will form proportions. So can I compare GH to GI? No, I want its mate from the other triangle. GH compared to KJ. That gives me a 12/8. Same thing with the other one, GI compared to LJ would give me 15 to 10. And all of those are basically given, even though I almost feel like I would tend to write this as a step 2, and I would say something like proportionate sides if they're similar. If I can prove the math works, then I'm proving it basically backwards. So can I get that these are the same? 12 over 8 reduces to, by 4, that would be 3 over 2. 15 over 10 reduces to, by 3, no, I'm saying that by 5, sorry, 3 over 2. They are the same, therefore they have that same scale factor. They've reduced to the same numbers, so that means I am forming a proportion. If this is, I think that's what I would call my reason. It's a proportion. It just, the math works. So we're basically saying 12 over 8 equals 15 over 10. That's kind of the summarization here where I'm saying my proportion works. This is just my proving that the math works. So my step 3 would actually use this, and this is my reason. Step 4 would then say that the two triangles, as I need it to, GHI is similar to triangle JKL, and my reason would be, forgot to label that, I have, okay, so proportion means similar triangles, something along that line. They list that as side angle side. That's fine too, because you're saying side, a matching 30 degrees, and this side, because you used, either way, honestly, either way, side angle side also works.